All right, we're set up. Let's introduce our next speaker. His name is Filip Rezabek. He received his Master of Science in Communications Engineering from TUM in 2020. He's a PhD candidate currently at the Chair of Network Architectures and Services of Professor Kahle, and he mainly focuses on applied and threshold cryptography, trusted execution environments, and distributed systems resilience and robustness. And in his talk, he's talking about METHODA, the framework for distributed systems evaluations.
Great, thank you for the great introduction, Richard. And hello everyone, my name is Filip, and today, as Richard was mentioning, I will be covering actually our years of work that are currently called METHODA. And this is the list of authors on the latest version that we published recently. But overall, the framework actually that is already been built for the past 4 years during the run of my PhD has also many more co-authors that are basically not on the last work, but is definitely a work of many people that are contributing to the project, and also several of them actually are in the audience, and you can maybe see their posters that are in the second room. So today's focus is on the aspect of actually how can we use this framework in the domain of blockchains or in general distributed systems. And for that, I want to briefly motivate actually what are the open challenges we have there, what is our methodological approach to it, what are the design considerations we had to consider when it comes to the large-scale deployments coming from blockchain, and provide some initial validation of our approach to that, and hopefully also call for action when it comes to our future work, where I'm happy to also discuss how such framework that serves as rails for evaluation of various use cases can be used in your particular domain. So, as we have heard over the past several sessions, blockchains are in general large-scale deployment systems that are spanning hundreds of nodes that are distributed in a global fashion. Each of them, as we have heard, also depending has various configuration parameters, has different type of properties, and in general they're also combining different building blocks. By building block, I mean, for example, they have various consensus mechanisms, they deploy various additional primitives. For example, we have seen recently some of them are also having additional primitives like multi-party computation, threshold cryptography, TEs, and so on and so forth. And the motivation is how can we actually bring such complex systems to our local deployment and be able to collect interesting insights from these systems. So there are definitely many layer 1 solutions, and also recently many L2 solutions, or even L3 and others, that of course provide the different guarantees when it comes to the transactions per second, latency, finality, and this part of the stuff that actually we will have to support as a part of our framework. We also see that there are always new use cases coming up to either mitigate or improve on the current state of the art when it, for example, comes to aspect of MEV, using some aspect of encrypted mempools, private compute and permissionless blockchains, rollups, privacy preserving aspects on the peer-to-peer layer, and many others. And in addition, each of the corresponding solution out there also has own configuration parameters that are often not clearly structured and provided basically ways on how did we actually reach to the final documentation aspects that are relevant for actually operating such a network. So of course we have different hardware specification and requirements. We have of course different types of network peer-to-peer structure. We have different block sizes, and of course as we see, the software themselves keeps evolving, and we always see new versions that are actually being deployed, providing a new set of features. When an example, when we compare Ethereum now and let's say 5 years ago, it will be very different chain with different properties that of course the framework should be able to assess and evaluate. So in general, the aspect that we want to focus on is to find a structured approach on actually how to assess the capabilities of various distributed systems, for example blockchain, but not only limited to that, we also consider other cryptographic protocols, peer-to-peer systems, and privacy preserving system in a reproducible fashion, be able to confer the different architectures and basically the implications on the performance of the system, and identify a common ground for evaluation without any external noise. Especially the aspect of external noise is the motivation why we are using private deployments in our local infrastructure. And for that we are focused on, of course, having the aspects of the real-world deployments out there and be able to consider all of these aspects of the real-world deployments in our environment. So for that, I will also provide some use cases later on that we are considering, but in general, we are also running additional infrastructure to be able to collect such insights actually from mainnet deployments of various blockchains and try to bring this information into our local evaluations in order to collect valuable insights. So here a bit of an overview when it comes to some scenarios we can consider. So we have, for example, two blockchains with very different consensus mechanisms and different properties, and we of course want to find some common ground for their comparison. We are also considering the life cycle of the transaction on the blockchain. So for example, the transaction is being generated by a single peer. It later has to propagate through the system. Do, for example, the individual peers in the system propagate it, or they just maybe drop it because they already have seen the message? How does it affect the overall performance and the load of the individual peers? When it comes to also the hardware specification, because of course each system will be slightly different when it comes to the hardware specification. We are talking that way about heterogeneous hardware setup. Each of them will also have different type of network properties when it comes to the uplink and downlink, depending on where you are running your infrastructure. And for that we want to, for example, collect the insights of the overhead on each peer. The peer-to-peer network structure may actually vary quite drastically among different chains. You might have some form of centralization where you have maybe centralized relay peers, or you have fully decentralized peer-to-peer network relying on gossip. And other aspect that of course is, even when we talk about transactions, what type of transactions are we considering? Do we talk, for example, about typical token transfers, or do we actually consider smart contracts with some complex logic that has to be executed on the individual peers? And of course, some of the talks we have here previously regarding threshold and MPC cryptography protocols, zero-knowledge proofs, and many others. And also when it comes to the last talk regarding deepins, definitely the focus on the infrastructure layer is very important. Also when it comes to the guarantees that basically it can provide to the upper layer aspects. So all of these scenarios basically is something that we are considering when we were working on our framework in order to be able to assess it in a local deployment. So for that, as we know, of course, such large-scale deployment systems are building on top of the internet infrastructure. So this is basically something that is not really necessarily part of the figure here. And we, of course, have to consider all of the individual layers of the TCP/IP stack when it comes to the physical layer. We have to consider the aspect of the infrastructure layer. How are actually the corresponding systems being deployed? What type of networking protocols are there? Transport layer protocols, and especially what is, I think, the most interesting aspect, and that is what we have heard in the past days, is on what is happening in the application layer. But of course, what we want to achieve is a combination of the individual deployments in our local infrastructure and be able to collect insights from each of the layer, ideally individually, but also in a combined fashion. For that, we are considering several deployment strategies. Mainly, we are focusing on the local deployment, but also recently, we are considering cloud deployment because it can also provide additional set of features when it comes to such solutions, and also it can improve on the realism when it comes to various types of latencies that can be introduced. And as we know, many of the permissionless systems out there are actually relying also on the cloud infrastructure as it is to actually operate their peers, and it's interesting to see how does it compare to the local views. We of course also have to consider some aspect when we are designing our experiments on how to do it. So of course we have to do our work before in the theoretical fashion to basically assess and model how such systems can behave. So for that we, for example, need to understand in detail how the consensus behaves in order to be able to design valid experiments to collect such insights from the local deployments. And also depending on the system, we either consider black box or white box testing, depending on how open the system is and how frequently it's changing. So on that front, of course, you can imagine that we especially focus on the black box testing for blockchains because we ideally want to deploy the system, interact with it, collect the insights instead of modifying actually the code base of the individual solutions out there, because they will basically become obsolete by the time we do our first commit. Because if you look, for example, on the frequency of new commits and new versions being released on various protocols, it's quite frequently changing. It of course brings a challenge to us as well to make sure that our results are still relevant in the longer term. And of course, I will not go through the individual parts. You can imagine that we want to collect various metrics from the system. I already covered some of them when it comes to latencies, TPS, and many others. And of course, we want to have the granular control over the experiment parameters in order to be able to collect various insights of the system performance. So we want to have the option to modify the number of peers, consider different threshold values when it, for example, comes to the system itself, change the runtime configs, modify message sizes, and many others. This aspect is orchestrating from the management host. Basically, already we have additional framework at the chair called plain orchestration service that was deployed by the colleagues that provide us the access to the individual machines. And on top of that, we are defining our experiments when it comes to the individual aspects of the stuff we want to deploy. And later on, we have the system under the test that basically is comprising of the various validators, client nodes, partial signers, network nodes, you name it, depending on what is the stuff you want to evaluate. And of course, we later want to collect and evaluate the artifacts and store them again for the reproducibility aspect that is very important to us on the management host, and of course collect the insights when it comes to the collection of the data itself, like for example how the system behaved over the runtime of the experiment itself. We have defined several experiments that I will be briefly talking about on the upcoming slides, but of course there is more than that also in the publication that we have as a preprint available. So I will be mainly talking about the evaluation and the overhead caused by the latest generation of trusted execution environments, cover one aspect of threshold cryptography, namely the threshold Schnorr scheme, and also assess our work that we have done when it comes to evaluation of MEV behavior on Algorand, for example. That could serve, I think, as a good case study on how the framework could be used also for other deployments. But in general, the list of the features that is actually supported is much wider. Just of course, due to the time, we don't have time to go through all of them. Some aspects we are considering is measuring end-to-end latency for the interaction of, for example, the behavior of client nodes on Ethereum ecosystem to basically see how does the peer-to-peer network behaves when we are reaching the mempools and how long does it take. Modification of hardware specification and their impact on the performance of the system, peer-to-peer networks, zero-knowledge proofs, and many others. But overall, we see that some of the aspects that we are covering are basically validating that our approach for such deployments provides valuable insights. So starting with the first results, it's just a high-level overview when it comes to the computational overhead introduced by the TEs. So the framework itself is supporting various types of deployments. So we are able to deploy on a bare metal, but also support various virtualization technologies. Namely, it's LXC, the Linux containers, it's Docker, Kata, and also Kata container running inside of the trusted execution environments. And in these figures, we can see on the left side an experiment that is stress testing CPU with compute-bound experiment focusing on the triad approach, where we can see on the y-axis the execution duration of time, and on the x-axis we can see the data set, the log size. And as we can see, especially I think here the focus is on the TE, we can actually see that they are quite nicely following the same pattern for the other technologies. So that way, basically, even if we run our experiments inside of a trusted execution environment, the particular one is AMD CVSNP, which is the latest generation from AMD, doesn't introduce additional overhead on the compute-bound experiments. On the right side, we are looking also into CPU evaluation, but this time on a memory-bound result, where we are playing around with different metrics dimensions. And again, here the focus is on the aspect of the implication of metrics dimensions. And again, we see that actually the latest generation is providing quite a comparable solutions. And of course, such type of insights can later on help us, for example, when it comes to deployments of some form of DeepIn or other, when it comes to ensuring confidentiality of data and providing insights into such use cases where, depending, for example, on how complex is your system and others, you can basically see if actually it's feasible and the cost you have to accommodate for using such type of technology. Second one is, I would say, closer to me, just since we don't have time to dive into it in so much detail, just want to provide a high-level overview. In this case, we are focusing on micro-benchmarking or a threshold signature scheme called Frost. For those who are not familiar with threshold cryptography, providing a bit of a context, the general idea is that you have several peers that are basically later on, after you run distributed key generation protocol, are later on ending up with corresponding partial key shares that are later on used during the signing phase to generate partial signatures, and later on these signatures are combined into a full-fledged signature that later on is presented to the external parties. So that way it's improving on the availability of the system because you don't have a single point of failure, but it's also improving on the unforgeability because, of course, you would have to compromise threshold number of peers in the network in order to get a hold of the private key. And in general, when it comes to public key cryptography, we have 3 main steps, right? We have the key generation, signing, and verification. With threshold cryptography, depending on the scheme, there is basically the modification have to happen on the first 2 steps, which is key generation and signing, but also depending on the scheme, for example, if they are non-deterministic, meaning that we have to generate some additional nonces, there also has to be the pre-processing phase where we are actually generating these random nonces that is taking additional overhead. And for this particular case, the threshold Schnorr schemes in a distributed fashion actually requires it's non-deterministic, so we need to pre-compute the additional nonces. And for that, basically, we can see a mapping of all of these individual steps on the micro-benchmarking level on how expensive it is. So from that, we can see when we talk about the participation creation, which basically is mapping to the key generation and the corresponding grounds, we see that this is rather cheap operation in order of microseconds for the corresponding system, but of course this corresponds to the local peer deployment. And then when we look at some of the more expensive operation, we are basically talking about the verification of the individual shares. So this is still part of the key generation, but basically everyone is later on verifying that these shares are valid among the individual peers. And lastly, during the verification, when basically we are collecting all of the individual partial signatures from the peers, we see that the verification step on the system is a bit more expensive, because especially considering if you would consider deployments of hundreds of peers, this can grow rather to a high number for the individual partial signature shares verification. So basically these are some aspects that can provide insights on how expensive such operation can be, especially if you want to integrate it, for example, into the stack of individual blockchain applications. And the last one that I want to briefly talk about, we also have a publication with a colleague, Burak, who was the first author, was an evaluation of MEV behavior on first-come, first-served blockchain, where we are having a theoretical understanding on how the network behaves, and for that we have devised a certain set of experiments that were later on deployed in our private network, where we were interested in actually understanding on how the relay, that is basically playing like a crucial aspect of dissemination of the individual transactions and blocks in the network, can actually affect the ordering of the transactions inside of a block, and how it can actually later on translate to the behavior of the MEV game played on the mainnet itself. So we have simple scenarios that are basically getting more complicated over time, where we just basically are firstly evaluating, okay, if we introduce a latency between a participant and the relay, and we don't introduce any latency for the other participant, how does it actually affect the ordering of the transactions inside of the block? And then we are also later on playing with stakes. So basically see, okay, we are not only introducing latency, but also we are introducing different distribution of the stake in the network. How does it actually affect the ordering? And later we have the combination of mainly focusing on latencies with in connection to other peers, and basically see how does such type of latency that has to maybe jump over multiple hops, but with a rather faster path, can actually affect again the ordering of the blocks, which help us to collect insights and verify our theoretical understanding of the protocol, that later on we were able to apply and explain actually our results and collection of such evaluations of MEV on the mainnet itself. So there where we can kind of see the interesting combination of both aspects. With that, I would be coming to the end of my talk, where I introduce a configurable framework that is providing, I would say, quite granular control, and it can be used to collect diverse insights. We are also able to scale to accommodate for large-scale deployments, so our system can scale to hundreds of nodes, of course, depending on how long you want to wait for such deployments, but we are still working quite heavily on improving the usability when it comes to deployment of such system, but we can see it's supporting the scale. And we, of course, see several open challenges, especially when it comes to the evaluations of various blockchains. We see that there is no clear set of scenarios that could be used and defined and used on when comparing different solutions. So this is something that actually we try to work on in order to define set of workloads that later on can be used and evaluated on different chains. That I think will be something interesting also when it comes to the comparison for the general audience. Basically, that is later on supposed to use the system because, of course, based on the aspect on how the system performs and the fixed conditions, you can actually collect insights into the usability of the system and also identify possible bottlenecks. So this will be, I think, something call for action also between the academia and industry, where we can look for such type of synergies. And overall, we believe this is a good stepping stone to achieve a holistic view on the interaction among the individual layers. So for example, later on, if we want to run something like a private computer and permissionless blockchains, we have the views from the local view of the TEs. Later on, we can deploy our blockchain node or other type of node inside of the TE, and we can see how does it affect the overall performance. So that way we can see the combination also from the various layers combined together. So I think this could help to develop and educate the new generation of core developers that can basically later on handle the complexity of always growing basically complex systems already with additional features and set of complexities being added to that. So for the future, just maybe some motivational words. There is definitely new use cases we can consider. We definitely are also considering the aspects of Deepin because there is a lot of building blocks that are basically part of it that could be used. And also as a part of future collaboration, definitely comparing and maybe simulating some of these large-scale deployments and comparing it to our emulation infrastructure would be something interesting. So with that, I would like to thank you for the attention, and if you're interested, here is a QR code linking to our publication, where we are describing more stuff in a bit more of detail. Happy to reach out. Thank you.
Great, thanks for the talk. Do we have any questions from the audience? Any direct questions? If we don't have any, yeah.
Thank you for the talk. Mm-hmm. Have you considered or evaluated some of the blockchains in the Hyperledger Foundation, especially Hyperledger Indy? Do you have some insights to share?
We haven't evaluated those because we are so far mainly focusing on the permissionless blockchains, but definitely the way how the framework is structured, it will be possible to deploy also permission-based solutions. Just we didn't find it as of now as a priority, but it definitely would be something that we could look into in the future.
Do you have time for one other question?
Yes, sure.
Okay. Second question would be, the topic was much more on the network design and analysis on a permissionless, let's say, blockchain. Mm-hmm. How would business logic affect certain blocks and some of the aspects? So have you tried to see the business logic also impacting the network?
So we don't have a particular, let's say, I would say, insights for that, but definitely what we can envision that it's possible to do is, like, for example, deploy any type of smart contract basically that's out there. We can just easily deploy it locally and evaluate its behavior. So this is definitely something we could do. And second part, we can kind of look into the aspects on how does, for example, the logic of how expensive is the logic of such smart contract with respect to usability, and also the overhead on the individual peers is definitely something that already we have basically in place. And now it will be just basically bridging these individual parts together. Okay, this is my particular logic, this is the particular stuff I want to understand and how expensive it is, and try to map these two things together. So it's definitely possible.
Yeah, because of the gas value, I think it might be interesting to see where you might become, whether there's an issue or not. Thank you.
Thank you for the questions.
All right. Any further questions? Doesn't seem to be the case. One more.
You mentioned the DP infrastructure. Do you envision this sort of peer-to-peer networks as an evolution somewhere, like turning into something different from what we know right now as the peer-to-peer networks?
That is a good question. I think there is already some tendencies in this direction when it comes to a lot of discussions of maybe some distribution of caching, right? That, especially when it comes to data availability discussions on Ethereum, right? I think that not all of the peers will, for example, necessarily have to have the data. Only some peers will need to see the data. And it will be interesting actually if Deepins can maybe play a role, because of course they provide a lot of storage, right, capacities, especially when it comes to Filecoin and others, that maybe could be also used to caching of such information for further usage. So I think there could be quite some synergies when it comes to that, especially it's providing a lot of incentives for people actually to make sure that they still have the data available, right? Because otherwise they will get slashed or they will just not get the financial support. So I think this will be interesting synergies on that front. So definitely something I think to investigate further.
All right, then I guess don't see any more questions. So we thank our speaker very much.
Thank you.